This lecture is on section 4.1 from Math 311, a course in linear algebra at Western Illinois University. So we are starting a new chapter and a new section, and it's really all going to be about eigenvalues and eigenvectors. So we want to look at linear transformations and their matrices a little bit more and get a little more information about them. And I want to start by looking at two examples. The first one is the linear transformation, which is just it goes from R2 and R2, and it's a reflection through the x-axis. So it sends the point x, or the vector xy, to the vector x minus y. So t of xy is x. T of xy is x minus y, and we know now how to find the standard matrix. Would be that standard matrix would be 1, 0, and 0 minus 1. And we have that that in particular there's going to be some there's a specific set of vectors that are fixed. We can see that any point on the x-axis is going to be fixed by this reflection, right? It won't go anywhere, and that this basically corresponds to a point with a 0y coordinate. So we can certainly see that t of x0 is just going to be x0, okay? Right, because minus 0 is 0, okay? We can also see that if we take points on the y-axis, then these just we are basically we're reflecting it through. So we're getting a point. We're keeping the x coordinate will be 0, and we're just changing the sign of the y coordinate. So t of, let's say, 0y is going to be 0 minus y. All right. Now, what's so special about these two cases? Well, x0, to no one's surprise, is going to be the same as 1 times x0. And 0y is going to be the same thing as negative 1 times 0y. Okay. And we have that, and that this is what this matrix is. So we actually have, just on this a vector of this type, t basically acts as multiplying this vector by a constant, namely 1. And for a vector of this type, t basically acts on it by multiplying it by negative 1. Okay, and this is, by the way, this is the same thing as saying that 1, 0, 0, negative 1 times x0 is 1 times x0, and 1, 0, 0, negative 1 times 0y is going to be the same as negative 1 times 0y. Okay. So we have this case now. We know in general, of course, that a linear transformation. We know that if a function that multiplies a vector by a constant, that's going to be a linear transformation. That's easy to check. Now we know most transformations don't act that way, but it will. It will find that for certain vectors, if we just restrict the transformation or the matrix to vectors of a certain set or a certain type, it does act as multiplying those vectors by a constant, and the constants might be different, like they are in this case. In this case, it was 1. In this case, it was negative 1. Let's see if the same phenomenon happens in this next example, where we have a projection of a vector onto the line y equals x. Now, let me just recall how this formula comes about. So if P is the transformation that takes a vector in R2 to a vector in R2, where basically the vector v is being sent to the projection of v onto d. Okay, where of course what's d? D is the direction vector of the line y equals x. So d is just 1, 1 in this case, and v is going to be xy. And remember that this is v dot d over d dot d times d. Okay, and that's how we get this formula. Okay, and this formula gives us this matrix. We can see the matrix here is just going to consist of it's a 2 by 2 matrix where all the entries are 1/2. Okay, now but geometrically we can sort of see which vectors are basically fixed by this, because we can see if we take any vector that's embedded on this line, the projection is just going to be itself, right? There's basically nothing to project. So remember, this is the line y equals x, so we can see that p of xx is just going to be equal to itself, xx. And similarly, we can see that if we take the line that's perpendicular to this line, y equals minus x, and we take a point or a vector that's embedded in this line, the projection is just going to be 0. So we have p of x minus x is going to be, well, it's 0, but it also you can see that this will be 0 times x minus x, and this will be 1 times xx. Okay. So once again, for a certain set of vectors, this transformation just acts like multiplication by a certain constant. Okay, in this, and of course this still has the effect of this would be the same thing as saying that this would be the same thing as 1/2, 1/2, 1/2, 1/2 xx, and this would be the same thing as 1/2, 1/2, 1/2, 1/2 x minus x. Okay. All right. Well, so we'd like to see what's the bigger picture on this. So we're going to see that we have a special term for these vectors and these special vectors and these special constants. So that leads us to our first definition. And we are not really going to be talking about this as in terms of linear transformation anymore, but we're going to talk about it in terms of matrices, even though, of course, every matrix is going to correspond to a linear transformation. Every matrix is a standard matrix for some linear transformation. But anyway, if A is an n by n matrix, we say an eigenvalue of A is a scalar, lambda, such that AV equals lambda V for some non-zero vector V in Rn. And if a vector exists, it's called an eigenvector of A. Okay, so a couple things here. By scalar, we mean this can be a real number or a complex number. We're going to allow complex numbers now. And when we have complex numbers, we can do, everything carries over. It's just, when you're adding and multiplying entries, we're just doing it in complex numbers if need be. An important thing about this is that the eigenvector has to be non-zero, because obviously when V is 0, this is always going to hold for any A and any lambda. So an eigenvector has to be non-zero. All right. Now, if we go back to our first example and we look at the our original transformation, that is the reflection through the x-axis, this was the standard matrix. Now we would like to rediscover what were the eigenvectors and eigenvalues. We saw in here, we saw that the eigenvalues were 1 and -1. And then the eigenvectors were, and for 1, it would be any vector that's in the form of x0 when x is not 0. And the eigenvectors for -1 would be 0 and y as long as y is not 0. Well, let's say we didn't know that, and let's say we wanted to check this out again. So what we're trying to find is a vector xy so that this matrix times xy is equal to lambda xy. Okay. Well, what is this? This is the same as x minus y. And then equating the two components, we get x equals lambda x, and y and minus y is equal to lambda y. All right, now you can look at this first equation and say, okay, well, lambda must be 1, and that's true. Or you always have to keep in mind x could be 0 before we divide by anything. We like to divide both sides by x, but we can't if x is 0. So this first tells us that either lambda must be 1 or x is 0. Okay, and if lambda is 1, we can see that well y negative y equals y is going to imply that y equals 0. And if x is 0, this tells us lambda can be anything, but then that means negative y equals lambda y, and x and y can't both be 0, otherwise we wouldn't have an eigenvector. So if x is 0, y equals lambda minus y equals lambda I means that lambda has to be negative 1. Okay, so the eigenvalues, so we have, to list the eigenvalues, we have lambda equals 0, and lambda equals 1, my bad, and that gives us y equals 0, so the eigenvector, well, certainly 1, 0 is going to be an example of that. Okay, that would be, solid, one of many eigenvectors. And then when lambda equals negative 1, right here we saw that x had to be 0, so and y could be anything, so we could take 0, 1. Right. So these are our eigenvalues. These are the corresponding eigenvectors. And by the way, it's not any coincidence that this is that 1 and minus 1 are the diagonal elements. We're going to see later on that when you have a diagonal matrix, the diagonal entries are precisely going to be the eigenvalues. We'll see that later. Okay, let's look at the next, going back to example 2, which was the projection with the line y equals x. If we wanted to go ahead and set this up the same way, so we have 1/2, 1/2, 1/2, 1/2 xy equals lambda xy. And multiplying things out, this is going to be 1/2 x plus 1/2 y equals lambda x, and 1/2 x plus 1/2 y is equal to lambda y. And we can see, we really don't have to go too much further to see that because this equals this, that means this has to equal this. So we get that lambda x equals lambda y. So you can say that, well, either if lambda is not 0, that means that we can divide both sides by lambda and we get x equals y, in which case lambda would have to be 1. And then, of course, if lambda is 0, if lambda is 0, you'll see what happens. So let's just do it this way. We can say lambda x minus lambda y equals 0. So lambda x minus y equals 0. So either lambda equals 0 or x equals y. For lambda equals 0, we can see that from this first equation we get 1/2 x plus 1/2 y equals 0x. So that will just be 0. So that tells us that y equals minus x. Okay, so that tells us x can be anything, but x can be anything, but as long as y is minus x. So, for example, so negative 1 would certainly work. And in the case where x equals y, we can see that, well, if x equals y, then we get that then 1/2 x plus 1/2 y is just 1/2 x plus 1/2 x, well, equals lambda x. Okay, and so we get x equals lambda x, so x equals, or lambda equals 1. So lambda 1 is going to be the other one, and the other eigenvalue, and we get the corresponding eigenvector will be 1, 1 among many. Okay. And that's exactly what we saw last time, right? We saw that and yeah, that we got, you know, we had one value where we had the eigenvalue was 0, and the other case where the eigenvalue was 1. And for when lambda was 1, we got something like in the form of 1, 1. When lambda equals 0, we got 1 minus 1, okay, which is what we have here. Okay, let's do another example. A new matrix here. So which will be a little bit more interesting. We do the same. So let's say we want to find the eigenvalues of and the eigenvectors of 2, 1, 0, 3. Okay, so 2, 1, 0, 3 times xy equals lambda xy. So this is 2x plus 1y equals lambda x, and 0x plus 3y equals lambda y. And we can see right away from this first equation, or rather the second equation, that either lambda equals 3 or y equals 0. Okay. If y equals 0, we can plug that back in here, and we get 2x equals lambda x. So either lambda equals 2 or x equals 0, but x can equal 0, x and y both can equal 0, because we want an eigenvector, so this means that lambda equals 2. So the eigenvalues are going to be lambda equals 2 and lambda equals 0. Or I'm sorry, lambda equals 3. All right. And when lambda was 2, we could see that y had to be 0, and x could be anything. So we have 1, 0 would be a possible eigenvector. And when lambda was equal to 3, when lambda equals 3, we can plug that back in here, and we'll get 2x plus y equals 3x. And so we subtract 2x from both sides, and we get y equals 3x minus 2x is x. So x and y have to be the same. So the vector 1 will work fine. Okay. So this is the eigenvector for 3. This is the eigenvector for 2. Okay. And of course there are many others that are possible. Okay. All right. Now let's look at an even more interesting example. Let's say we want to find the eigenvalues and eigenvectors of this matrix A, 1, 2, 2, 3. All right, so let's set this up the same way. We set 1, 2, 2, 3, xy equals lambda xy. And then this gives us x plus 2y equals lambda x, and 2x plus 3y equals lambda y. All right, now at this point we got to be a little careful. This is not a very typical. We're not just solving your usual two equations and two unknowns linear systems. linear system of equations, because there's actually 3 unknowns when you include the lambda. So we have to do things be a little more careful here. And what we'll do is we're just going to try to use some substitution, right? X in terms of y, or y in terms of x, and lambda, and hopefully see where that leads us. Okay. All right. So from this first equation, if we collect the x terms, we will get that 2y is lambda x minus x, or 2y is going to be x times lambda minus 1. Okay. And then from here, if we collect the y terms together, we get 2x is going to be lambda y minus 3y, or 2y will be y times lambda minus 3. All right. So now let's see if we can write these together. By the way, we should say we can take this first equation, divide by 2, and we'll get y is going to be lambda minus 1 over 2 times x, and take this this equation right here. This should, by the way, this should be an x here. Divide both sides by 2, and we'll get x is lambda minus 3 over 2 times y. And so y will be lambda minus 1 over 2 times x, which is lambda minus 1 over 2, and x is now lambda minus 3 over 2 times y. So we get that y is going to be lambda minus 1, lambda minus 3 over 4 times y. Okay. And we can see that, okay, so either this expression here has to be equal to 1, or y is going to be 0. But if y is 0, that means x is 0 from here, and we can't have both of them being 0. So this tells us that 1 has to be equal to lambda minus 1, lambda minus 3 over 4. And let's multiply both sides by 4. And multiply this out. Get lambda squared minus 4 lambda plus 3. All right. And then subtract 4 from both sides, and we get 0 is lambda squared minus 4 lambda minus 1. All right, now you'll see that this is a quadratic equation, and even if we can't factor it, we can use the quadratic formula. Remember the quadratic formula? It is, for solving ax squared plus bx plus c equals 0, the solution would be minus b plus or minus the square root of b squared minus 4ac all over 2a. So in this case, we see that a is 1, b is negative 4, and c is negative 1. And plugging this in, we'll see that lambda has to be minus 4 plus or minus the square root of minus 4 squared minus 4 times 1 times negative 1 all over 2 times 1. This will be 4 plus or minus the square root of 16 plus 4, that's 20, all over 2. And this reduces to 2 plus or minus the square root of 5. Okay, that's lambda. So we actually get 2 values of lambda, 2 eigenvalues, but they're just irrational this time. Okay, but we can still find out let's see if we can find what the eigenvectors are. First, if we let lambda equal 2 plus the square root of 5, we can see that, well, let's see, let's write y. We can see here that y is going to be lambda minus 1 over 2 times x. So y is going to be 2 plus square root 5 minus 1 over 2 times x. and this is going to be 1 plus the square root of 5 over 2 times x. Okay, so x can be anything we want as long as y is 1 plus square root of 5 over 2 times that. So a perfectly good eigenvector would be if we let x equals 1, then y is 1 plus the square root of 5 over 2. And that would be the corresponding eigenvector for this eigenvalue. Incidentally, 1 plus square root of 5 over 2, that's the golden ratio, by the way. That comes up a lot in stuff in mathematics. Okay, if we do the other eigenvalue, 2 minus the square root of 5, do the same thing. Y is going to be, once again, lambda minus 1 over 2. So this is 2 minus the square root of 5 minus 1 over 2 times x. This will be 1 minus the square root of 5 over 2 times x. Once again, we can let x equal 1, and an eigenvector will be 1 minus the square root of 5 over 2. So that's a perfectly good eigenvector. Okay, there are many others. Obviously, any scalar multiple of these eigenvectors will also be eigenvectors. You can convince yourself, or we can prove it later. And just to show you that this actually works, let's go to take this vector and multiply it by our original matrix. Okay, this is going to be 1 times 1 plus 2 times 1 plus square root of 5 over 2. The 2's will cancel and we'll get 1 plus square root of 5. And then if we multiply, next we take this row, this vector, 2 plus 3 times 1 plus square root of 5 over 2. We get that. And this will be 2 plus the square root of 5. And this, if we get a common denominator, this is going to be 4 over 2 plus 3 over 2 plus 3 square root of 5 over 2. So this is going to be 7 plus 3 square root of 5 all over 2. And believe it or not, this is actually going to be 2 plus square root of 5 times 1 plus square root of 5 over 2. If you're not sure, if you don't believe me on that last one, I don't blame you. But if you just multiply 2 plus square root of 5 times 1 plus square root of 5 over 2, you'll get 3 plus 5, I'm sorry, this is 2, and this is 5, so that'll be 7. And this will be 1 square root of 5 plus 2 square root of 5, that's 3 square root of 5, okay, all over 2, which is this. Okay. So this is an eigenvector. This does work, and you can also check that this matrix times 1 over 1 minus the square root of 5 over 2 will be 2 minus the square root of 5 times this. All right, so now we're going to, before we quit this video, let me just show you this quadratic equation is going to be a very, very important one. This is an example of something called a characteristic polynomial, and we're going to see that for every matrix, it's going to have its own characteristic polynomials, in which the roots or the zeros of that polynomial will be the eigenvalues. Okay, and in the next video, we're going to see what just sort of generalize what we did here to find a more general way to find these eigenvalues, besides going through all of this stuff. This is perfectly fine, but we're going to see a more standard way of doing that in the next video. So we will see you next time.